Hello, I'm Emmanuelle Lamarche, and this is my lab 3 for Physics 2112. And in this lab, we looked at the effects of magnetic field from a bar magnet at different distances from and so some of the important concepts from class that we applied in this lab were the magnetic field due to dipole. We used the Biot-Savart law with this equation that generalizes for dipole on and off axis. And we also looked at the distance dependence of a magnet, which has an exponential format. And these are the values that we derived experimentally. And we use the linearization of this exponential equation to really be able to compute those values. So the model that we used in this lab was with a bar magnet and then a magnetometer on my iPhone. And so we first calibrated the magnetometer and made sure that both the magnet and the phone were in line with, were perpendicular to Earth's magnetic field, so it wouldn't have those impacts from it, and we'd be able to just see what comes from just the bar magnet. So that's what you can see in the top diagram, and then during this we would move the magnet at certain distances to see when it's equal to certain magnetic fields without the impact of Earth's magnetic field. And we also made sure that the sensor of the phone was lined up along that same line as the magnet. And then we also did a few measurements off axis, and that's what is shown in the bottom model, where you can see that the phone was moved the same distance along and off axis. So from this, we graphed our results of the measurements at different magnitudes of magnetic fields, and we used the linearization equation so that we'd be able to compute the values from it. And using this linearization that we saw on the other side, where the y-intercept was ln of k and the coefficient for x is actually n, we found that n was negative 2.95, which makes sense because its magnetic field from a dipole is as a function of 1 over r cubed. And then we also rearranged from ln of k to find mu, which is the magnetic dipole moment. And this we did knowing that k was a combination of the coefficient from the Biot-Savart law and also because it was on axis, the dipole moment was 2 times the coefficient times mu, so we rearranged to find 2.06 for mu. And so some of the observations we made from the data we collected were that when the magnetometer is far away from the magnet, there's a near zero magnetic field in the x direction, and as the magnetometer moves closer to the magnet, the x component of the magnetic field increases, which makes sense because we know that when something is closer to a magnet, the field will be stronger because it has an inverse relationship with the distance. And so then we use GlowScript to actually visualize the magnetic fields at different locations and do that. And for this we use that Biot-Savart law for different observation points on and off axis. And we also did this at a 45-degree angle to see if the field at 45 degrees was where we expected it to be. And so these are the results that we found, and the code is in the description. So the questions to think about with this experiment are that if we hadn't oriented it to compensate for magnetic north, this would have affected our results a little bit because we wouldn't have started moving the magnet with a magnetic field of 0 magnitude, and so the Earth's magnetic field would have impacted the magnetic field on the magnetometer, so the results would probably have been less accurate. And also, if we were to stick 2 magnets together, we would probably expect our results to show that the magnetic dipole moment and the magnetic field would increase because the two magnets would have greater strength and a greater magnetic dipole moment. So this would make the magnetic field at observation locations on and off axis larger.